Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're gonna take a look at the most interesting topic, fusion power. So let's dive right into it. So just as last episode of Science Thursday I talked about fission where you break things apart, this is invert of it where you attach things, basically combine two light elements as in tritium and deuterium, combine them and then you get helium and one extra neutron. And as I said, like if you calculate the weight of these two parts versus weight of these two parts, there will be a bit of loss. Now this loss is bit more than what you get in basically uranium loss. So this gives you a lot of power, and this, if you want to calculate how much energy you're gonna get, we have Einstein to thank for that. E equal to mc square. Now be mindful, fusion can be done with almost everything from in periodic table given from top, as in like from hydrogen to helium, go down till iron. You can't go below iron or even at iron, because the moment a star starts to fuse iron, it absorbs more energy than it gives out. It's not exothermic anymore. It becomes endothermic. It takes energy. So star dies. So when you hear people say like, first it will go through hydrogen burning phase, it burns through the hydrogen, then it starts to burn through helium. It can keep going until it reaches in a stage in periodic table where there is iron. The moment it reaches iron, the star is dead from the inside. Now other things can blow it apart before that, but if you are writing a sci-fi novel, copyright me, show them that they have helium reactor or something heavier than that, because that inherently gives more power. Helium specifically, to give you an idea on context how much powerful helium reaction would be, is that if our sun started burning helium, which it will do when it starts to grow, its size will grow as as large as Earth's orbit. And heck, it can go even further than that. So that's fusion. You can do fusion till iron in the periodic table, and generally hydrogen is the easiest to fuse. So why the interest? Well, the fuel required for that, it's not like thorium. Even though India has a lot of thorium reserve, it's not like it's just laying around there. You can't just go and collect it. It requires severe mining. It's super abundant, and it's abundant in the universe. It's not like we are lucky to find it here in this planet. You will find it everywhere. So it's quite abundant, quite cheap. Second, this is the crucial aspect. This is the sole reason why anybody even cares about this, is 24/7 power. Basically what we call base load capacity. The solar, even though they are reaching a point where we call price parity, more about it in my video. Basically the cost of solar energy is reaching a point where more and more solar farms will be made, because it will be cheaper to produce electricity that way. Now everything is awesome about that. Only problem is what you're gonna do at night. Wind is nowhere near price parity, and while when you can use wind power for serious load, it can provide some base load capacity. Does not have enough capacity to provide base load capacity for the whole planet or whole country's economy. So for that reason, base load provision of this is very crucial. Now second, we come to, it has no pollution. Basically it does not emit CO2 or methane or pollutants or anything dangerous. So that's awesome. And this is very cost saving aspect for us, is that it can be connected to current grid. Like a fusion power plant will not look any different from fission power plant. It will look just like this, and you will just have a giant power cable coming out of it, basically grid connection. So this is why there is interest. It will work on existing grid, does not require giant power storage. It will work with whatever we have already. It provides base load capacity, no pollution, so everything is awesome. Now let's do pro con this thing. Pro, it has raw power. Now this is crucial aspect of it. Even if you take fission and you make very good reactor out of it, I haven't come across any designs of reactor where you are expected to get more than 10-20 gigawatt. Like generally it's advisable to make multiple small reactor where you can contain the accident if it happens. So inherently the footprint of that power plant will become ludicrously large. Now of course it's nowhere near the footprint of a solar power plant, but inherently it's very big. So, and the fact that hydrogen is A, abundant, B, when it fuses it gives out relatively more energy than what uranium gives. It's inherently more powerful, as in multiple times more powerful, not hundreds of times more powerful. It's not like going from chemical to nuclear. It's like chemical to better chemical. So basically the difference between atom bombs and hydrogen bomb. and it's super safe. Now, crucial with fission, as I talked to you, is the best energy source we have. Only problem with that is it's a flat out intolerant of any mistakes. Second, it gives out radioactive waste, and the radioactive waste, aside from thorium reactors, are radioactive for thousands of years to millions of years. So suffice to say, it's ludicrously dangerous to use that. Now, right now we are stuck in between a rock and a hard place. Is that if we use coal power plant, we pollute the atmosphere that every single human breathes in, or we use a nuclear fission where we have to isolate an area where nobody goes in. I mean, even if somebody goes there, they die from radiation poisoning. However, it has no effect on wildlife. Look at Chernobyl; it has become a freaking wildlife sanctuary because plants can handle radiation much higher level than we can. And the fuel is super cheap, so there is no risk of that. So safety first, awesome. And fuel can be extracted from seawater. I'll talk to you about more that. Now, cons are it is still radioactive. The waste that is coming out of it is not radioactive. The reaction itself is idiotically radioactive. Like this part, I have seen many places skipped, sort of like the reaction that you are doing gives off neutron. Neutron, as many of you know, alpha, beta, gamma. It's gamma ray. Basically, it can emit gamma radiation. Heck, it can flat out make other things radioactive. Basically, if you have a chamber like this and if gamma radiation is releasing from here, over time the panels that you have will become irradiated. This is a serious concern with this. And what I'm referring to here is neutron flux. This is the core reason why nobody can just put normal steel here. Like this inherently is so complex that to put something there, it has to be designed to handle more radiation than it gets from normal nuclear fission reaction, because the density of neutron coming out can exceed that. And it's very complex. Like none of these things cost less than like $10 million. None of this is like even $10 billion. Like the amount of money we have spent just trying to make a experimental reactor is ludicrous. Now, many of you might say, okay, that's true with every technology. Like as technology gets further and further along, we might get cheaper and cheaper. Economy of scale kicks in. However, this will not happen with this. I'll show you why. Then we come to the cost aspect. Now this is crucial. As I already mentioned, solar has reached a point where it's reaching what we call price parity. So it will be cheaper in future to generate your electricity from solar. That's why India already finished, I think we have already reached 3000 megawatt capacity, and one of our farm recently finished was 800 megawatt. Another 10,000 megawatt farm is just being built in Rajasthan. It should be finished by 2025. And China is also building solar farms that are like rated for 20,000 megawatt or something like that. So suffice to say, as you can see, China does not care about environment, but they have to care about economics. It's becoming cheaper to produce electricity using solar cell. So, and if you have desert or uninhabitable lands, basically where people cannot live, you will be in a scenario where like just use it for solar power, even because most of humanity's power consumption happen during the daytime, so it's generally wise to do so. The reason why I said the cost of this will not be cheap inherently is because this has what's called superconductors and cryogenics. Now, how they are achieving fusion? A is they are creating a plasma. As many of you know, plasma is the fourth state of matter. Basically, electron is split from the nucleus. So what they get is raw, and it is electronically charged. Basically, it has positive or negative charge. Benefit of that, we can control it using magnetic field. Now, this is that magnetic field generator. Now, that's a cut section of a tokamak reactor. This is an advanced tokamak reactor design where they are twisting the magnetic field such a way that at the point of twist where they were twisting, they'll get a lot of fusion. And when I said the fuel is abundant, that's mathematically true, however not absolutely true. The reason for that is that it uses a rare isotope. When you take hydrogen, normal hydrogen, it does not have the isotopes that we need for fusion. Deuterium and tritium, they are rare isotopes. Of course, one is much more rare than other one, and we haven't reached a point where we can just do electrolysis, get the water, get hydrogen, and do fusion with it. We haven't reached that point yet. And the electronics needed for this is very complex. Not to mention, material engineering is the biggest hurdle of this, is because I already mentioned everything built here has to handle insane amount of neutron flux, and that can destroy things from the inside, as in on a molecular level it can destroy things. So building something that can last for 10-20 years is very crucial. many things you have to also understand. This presents, as I talk to you, is the largest gradation of temperature existing in the universe, because one side, basically the side that contains the electromagnet, is at near zero, near absolute zero, as in like minus 230 degrees Celsius, and the core side where the plasma is, it's at 15 million degrees Celsius, which is hotter than sun's core, and it's also hotter than chronosphere of the sun. The reason why we need to go that higher is simply sun is getting the added benefit of gravity. Gravity is doing the crushing. Gravity is doing the main aspect of it. The temperature is not the crucial part. The gravity is that is crushing it so badly that before the temperature even reaches very high, it starts to fuse already. So that's why the cost is the crucial aspect of this technology. That is why I don't see fusion becoming the next power source. It could happen, but simply because if you go to a government, like let's say India is also investing a lot of money into this, and that tokamak reactor that is being built as of now for large scale study, India is also playing a crucial part of it, and that neutron base plate is built in Bangalore, basically in India. Russia is also contributing a lot into this, China also. So suffice to say, all things considered, all analysis I have done as of now comes to a conclusion that is ludicrously expensive. Like, we haven't even built this, and the projected cost is already 10 to 30 billion dollar, and that's for a 500 megawatt plant. Like, if you spend that much money, you will get like a gigawatt size solar farms or gigawatt size wind farms. So basically, at the end of the day, money talks. So here, this is kind of weak. So what we expect in the future? Well, at best case scenario, first experimental trial actual reactor that is connected to the grid that can handle fluctuations should happen in 2050, hopefully. I will not put my money on it, but hopefully. Second, if humanity is to progress any further, actually become power independent, as in like, we don't have to worry about solar or anything like that, we have to have the ability to use normal vanilla hydrogen, not some freaking isotopes of that. The reason for that is those isotopes, even though we have enough of it, mining them requires, not mining as in like filtering them out is very expensive process, and not to mention they will run out at 1000 years. So we only have 1000 years of reserve. So we have to figure that out, that how to use normal hydrogen before that. Now, the reason why I'm making this video is that I think there is a hope that, as I already mentioned, temperature is not the key to everything. Either you can compress it such a way that it uses the compression force to bypass the Coulomb barrier, basically, where two protons basically do not want to hit each other because they are both positively charged. There is a barrier. Like, if you exceed that barrier, basically that's why we are heating it up so much, so that overpowers it. So once it touches it, your fusion is done. So to make sure it touches, either you make it very hot or you do what general fusion, link in the description below, they are trying to do. I am hopeful for that, is simply because they are using what's called plasma injection. Basically, they have a lot of piston, they will inject the plasma, and the plasma is not already fusing, it's there, it's normal, it's super easy to make. They will compress it using this pistons. As you can see, this is a small scale version, and once they compress it, this compression area that you are seeing is not vacuum, not like tokamak reactors. What it actually is a liquid metal, basically either lead, molten lead basically. So they will compress that, and due to that compression, the fusion will happen and it will give energy to the liquid metal. That way they also bypass the headache of dealing how the hell they're gonna deal with neutron damage. So basically that neutron is being absorbed by lead much more effectively, and because they are circulating the lead, they can add new lead if lead get destroyed on a molecular level or it gets radioactive. They can simply siphon it off from the reactor. So general fusion, I am more hopeful for that, because they have cheap design. Inherently, you cannot go to a small country or a developing country and say, give me $500 million or $50 billion, I'm gonna give you a power plant that barely gives you 1 gigawatt of power. So cost parity is crucial. So best case scenario, we get our first reactor in 2050, and I'm hopeful that we'll have cheap design. I am putting a lot of faith in general fusion design. Link in the description. So this was my presentation on nuclear fusion. I hope you liked it or learned from it. In that case, please like. If you don't worry about it, dislike it. Leave a comment what you want to see in the next episode of Future Friday, and subscribe, press the bell icon, as I make video every day. And as always, thanks for watching.